Okay. So just a little more equations. This is just elaborating what I just said. So you can ignore the mg subscript and just look at the equations for delta and theta. Theta is the divergence of the velocity. So for a metric like this, virtually any modified gravity theory still obeys the conservation of the stress energy tensor, which gives you the continuity in Euler equation. So these are unmodified, and the only thing we need to be careful about is that the potential involved is this Newtonian potential. As I said already, the two effective equations that describe the modification of gravity then come from the other components of the field equations, and they look like this. So that's sort of a complete set of equations to describe our four perturbations: delta, theta, phi, and psi. Right? So we'd like to learn about these guys, and you can think of them as functions of k and z that are unspecified. So how do we do that? Well, we'll see that delta and phi plus psi can be obtained from data. Okay, galaxy clustering plus lensing, or the ISW effect. So bias enters into the story, but delta and B can be measured simultaneously. So this is all in principle, okay. So two combinations can be measured from data. We have two conservation equations that are not modified. So that's four pieces of information that can be used to obtain all four variables. So in a modified gravity scenario where you don't have dark energy, you can in principle use measurements to infer these variables and therefore measure eta and G effective. So you could, for instance, do a test of general relativity, which is the first thing you'd want to do to see if eta is 1 and G effective is G Newton. This framework is a little bit simplified in that we have not assumed strong perturbations of anything like dark energy or couplings in the dark sector. That is, couplings of dark energy to dark matter or dark matter to visible matter. If you have these hidden couplings, then you can you need additional variables to describe them, and then you can't close the system with observations. Okay, so this is a simplified but still quite general and useful description in which to compare theories to observations. Of course, getting to this point for a modified gravity theory is highly non-trivial. When you modify gravity, you generally have field equations that are significantly more complicated than GR, and so it takes a bit of work to get this stuff. You can write down power spectra just to explicitly show how you'd relate observables to theory. There's a power spectrum of lensing and dynamics with these modified gravity parameters that I don't want to dwell on. What's my remaining time? That digression really cost me. Right. So this is a way of putting together how we can think about observations to test gravity theories. There's dynamical probes in blue that measure the Newtonian potential, and lensing and ISW that measure the sum of metric potentials in red. And you can see that now there's a place for galaxy scale measurements, cluster scale measurements, large scale structure measurements, and their combinations are the most powerful. So we start thinking about large scale structure differently, because to test dark energy, you just want to find the one best measurement that's the cleanest and works in this linear regime, and that's it, you're done. And nothing else adds much value. But when you want to include testing gravity, then you really pay attention to everything else. Okay, skip. As far as lensing goes, by itself it just measures the sum of these metric potentials. We don't know what they are separately. So you need to do a little more. You need to at least do tomography to see how this growth factor evolves with redshift. If you can relate it to matter correlations, then you can get G effective. But the most robust thing you can do is to use combinations of cross correlations, galaxy-galaxy lensing, and redshift space measurements. And that gives you the ratio of these metric potentials, which is completely model independent, and it's, at least in the models that are around now, is predicted to be significantly different from unity. By significantly, I mean like, what, 10%. So you know about redshift space distortions. You can use a redshift space measurement to get at 3 different power spectra, and we'll be interested in this middle one called PGV, the galaxy velocity power spectrum, measured from Sloan here, and in a recent paper, Reyes et al. Have combined that with galaxy-galaxy lensing to get at a 20% test of gravity. Okay, general relativity passed. Otherwise, you'd have definitely heard about it. So there's this test and a couple of others, but but this is very limited information that we have about gravity on large scales. So in the future, we want to do similar exercises, but with bigger data sets. So this is the kind of measurements we'd use from, say, the dark energy survey, lensing power spectra, cross power spectra, and the redshift space PGV from a survey like BOSS. So if you do that, then you can get constraints on G effective and eta. But just to show you that we are really in the early stages of understanding how to think about gravity. If you allow them to be time dependent, then the constraints you get are extremely sensitive to your fiducial model. They look really good or really bad, depending on what your fiducial is. So what do we know about gravity? Just to summarize in a slide, these red circles are current measurements. They're mostly at the 50% level in the space of redshift and length scales. And we really want to span this space to look for deviations. Because as I said, we don't know how the transition from gigaparsec scales to smaller scales occurs, so this entire square is fair game. So this is the recent Reyes et al. Measurement at 10 to 20 megaparsec scales, redshifts of 0.2 to 0.3, and we'll do, say, a factor of a few better with DES and BOSS, but we should, think about all these other spaces. The first quite interesting test of gravity came from strong lensing, the SLAC survey combined with stellar velocity dispersions. Okay, so we want to focus on this redshift range and this range of length scales for these linear regime power spectrum tests of gravity. Small scales are extremely interesting. So every modifying gravity theory must transition to general relativity. One of the really encouraging theoretical developments is the identification of somewhat generic mechanisms that make such a transition for high dimensional theories and for FFR. So these are so these involve identifying an additional field, a scalar-like field, that's involved in a modified gravity theory. And you can then think of that field as having a dynamics that's coupled to the gravitational field. And on small scales, so this is from a simulation where this is the density, this is the potential in 2 different models, but there's this other field that's coupled to the potential such that on small scales it changes the behavior of the potential. So we need to do some nonlinear calculations, include the coupling of these fields, and then we can get a rich phenomena out, namely the modification of the gravitational force that's dependent on the density and length scale that you're making the measurement in. Okay, since they're transitioning to GR and solar system scales, the easiest way to do that is to use the fact that a galaxy is order 100 times denser, 100,000 times denser than the cosmic density. So it's either the density or potential well that provides this transition to general relativity. And therefore, to get to GR in the solar system, you predict some interesting transitions from modified gravity that's possibly enhanced around halos, and then transitions to GR within halos.